Hi, everybody. Welcome to this webinar presented by VibraTec and Spin. Please, could you tell me if you can hear me clearly and see the screen? If you can say a few words in the chat so that everything is going all right. Okay, crystal clear. Perfect. So we can go on. I will switch off my camera just to be sure that you have the best connection as possible. So as you know, we are launching today a webinar series about the design, the manufacturing, and the validation of electric motors. Today, it's the first webinar. It's an introduction webinar, so we will give you an overview of what will be addressed in the next weeks. The presentation will last something like 35 to 40 minutes. And you can already ask your question in the chat or during the presentation or at the end of the presentation. And at the end of the presentation, we will have something like 20 minutes to answer your question. I will start by introducing the speakers. So sorry, I will start by myself. It's not very polite, but let's do it like this. So I am Sylvestre Lécuru. I'm the Automotive Business Unit Manager at VibraTec. I have 12 years of experience on e-drive project management, and I'm also a specialist of e-powertrain NVH, and our company, as you can see, is located in the southeast of France. And today, as a second speaker, we are welcoming Luigi Rizzi from Spin company, which is located in the north of Italy. Luigi is the engineering manager at Spin, and he has more than 20 years of experience in the field of electrical, mechanical, thermal design of electric motor, and also about manufacturing prototypes and testing it. So Luigi, we are very glad to welcome you on board. You can say hello to everybody.
Hello to everybody. Thanks so much for having me here.
Okay, thank you. And I think we can also hear you clearly. So to start the presentation, we'll have a few words about VibraTec company and Spin, and then we will address the topic of the day. So a few words about VibraTec. So our core business is noise, vibration, and structural reliability in the field of electric mobility and electric motors. We do some multiphysical design, so we're talking about electromagnetic noise, gear noise, for example. We can do also some tests on components or complete vehicles. And we can also do some neurotransfer thanks to our training programs, for example. I will give you some examples of what we are doing concretely. So this is an example of noise and vibration simulation on the complete e-powertrain, including the e-motor and the transmission, the gear transmission. So we have our tools called VibraGear and VibraVolt to do this kind of simulation. On the test side, of course, we do classic measurement, like experimental model analysis of component to improve the numerical models. We do also some vibration measurement, noise measurement. Here you can see an example of acoustic power measurement on an electric motor for hybrid application in our test bench in Lyon. So we have this capability also. And we do also test on battery electric vehicles. and hybrid vehicles. So it's kind of vehicle engineering. So we do some transverse path analysis. We have interest also in other kind of sources, for example, like the road noise or aerodynamic noise. And we have some knowledge and experience also in the powertrain integration, or to design the mount and the structure for this kind of component in the vehicle. And of course, if you want to learn more about our skills, we have a training program. Here I have presented some example of training program, one of noise from electromagnetic excitation, or on the vehicle powertrain integration. If you are interested, you can check on our website. Okay, so this was a short presentation. I will leave the microphone to Luigi so that he can present the spin, and then we will go into the topic of the day. So.
Thank you very much, Sylvester. Thanks for the introduction, and also for once more for the opportunity to be here. Let me try to share the screen. Just a moment. Okay. You should see my screen now.
Yes, it's okay. You can go on.
Thank you. Before to start, let me say a few words about the real reason why we decided to prepare these webinars. Around 7 years ago, I joined Spin, and we started this new trip in the world of engineering, which for me is very interesting and exciting. But if I go back in time, back then we were involved in the design of many kinds of motors. And every day we used to deal with problems like, for example, optimization of efficiency, better estimation of losses, demagnetization, and so on and so forth. So many things together. Then we began to investigate also the problem of vibration and noise. And we had a strong feeling that it was a serious issue, never completely solved. In most cases, the problem comes to light only during the testing stage, when a lot of money have already been spent, unfortunately, in design and also prototyping. Often, to find a solution, more money have to be thrown in, and is always a fight against time that may even worsen the situation. This, of course, also happens with many other difficult tasks related with the design of motors. The reason for this is maybe related to the complexity of the problem. Different skills are required to understand what's behind vibration and noise and what's behind all the other topics. So a strong coordination between various departments should be adopted. As you heard, my name is Luigi Rizzi, and I'm Technical Director at Spin. Our company has a long story in the field of engineering. Let me briefly show what we do. Okay. First of all, we design electric motors. We can guide you through the development process from concept to industrialization. We manage all the different topics related with the design of complex parts, and we also provide prototyping and testing services. In this slide, you can see two high-speed traction motors in a back-to-back configuration on the test bench. These motors are an example of a challenging application. Here we have 120 kilowatt of maximum power at a maximum speed which is 30,000 RPM. This speed allowed to reduce the size of the machine in less than 25 kilograms. But this result has been possible only by carefully balancing the need for high performance in terms of power density with the need for structural stability and also reliability, in which the mechanical design is a key point. A smaller version of this motor is now part of a hybrid propulsion system of a hypercar. Another example of challenging application is the axial flux motor. In the recent years, this motor has become popular for its very high torque density, which allows to reduce the mass and the size and makes it suitable for automotive, for example, and also aviation application. Here you can see two examples on which we worked. One is a torque motor for traction with a remarkable torque density, as you can see here. And the other is a pump for a cooling system, also in the automotive industry. The axial flux motor design poses several challenges, also related to the structure of the rotor. So a deep understanding of the dynamic behavior is a critical part of the development. Let's move on. We do also innovation. We cooperate with many Italian university and research centers in order to scout innovative ideas that can improve our production. As an example, we recently funded a PhD at the University of Padua with Professor Nicola Bianchi in order to study synchronous reluctance motors. Let me spend a few words on them. Synchronous reluctance motors are not new. They were initially developed in the 1920s, many years ago, but they were unable to achieve their potential until the advent of high-performance electronics. So today, they are an interesting alternative to rare earth motors with good performance and a really competitive price. And most of all, they avoid all the risks connected with the use of rare earth materials, especially the unpredictability of cost and also the availability of material. In particular, we developed an improved version with very low torque ripple, better efficiency, and also higher power factor with respect to conventional synchronous reluctance motors. Here you can see the basic data. If you want more information on this topic, feel free to ask at the end of the webinar. Then we also develop engineering software. As an example, we recently released the first version of a new tool called Swift, whose intent is to speed up the design process by simplifying and automating the computation of complex parts, like, for example, the axial flux motors. Here you can see the Swift user interface. The basic idea is that engineers should not lose their time by dealing with things like mesh setup, solver settings, or other similar tricky options that fill the common engineering software. But they should concentrate on the part that they are designing, looking at the results and taking decision. This is why we spend a lot of time in process automation to make things easy for the user. Last but not least, we also train people. We are a certified trainer for engineers involved in the design of mechanical components. Last year, we launched a new website called Spin Academy. Here you can find a lot of materials on interesting topics like the ones that we're going to discuss today, for example. Now, as I mentioned, any new design poses hard challenges. Some of them related with mechanical design and some other with electromagnetic and thermal design, for example. Let's start talking about the basic workflow and discuss a few key points that engineers should never forget to verify. First of all, the design process starts from the list of requirements that must be satisfied. This list may be really long, it is actually really long, but we can group them, all the requirements together in 4 main sections. Outline requirements defining the overall size and mass. Performance requirements, for example, defining torque, power, efficiency, and many other things. But also
it seems that we have lost Luigi. He's back.
something happened to my connection. I think.
We can hear you again, so you can
Can you
go
see
on.
the screen?
Yes, it's okay.
Okay, good. Let me go back here. So we were talking about requirements. So I said we can group them together in these 4 main sections. The verification of all these requirements normally requires many skills and complex analysis. But often, tight schedules forces engineers to find some easy way to deal with all the work ahead of them. Sometimes they take shortcuts by making assumptions or using their past experience. But this may lead to undetected issues, which will eventually generate huge problems. This is particularly true not only for NVH, but for example, for things like additional losses, demagnetization, PWM effects, and their impact on performance and reliability. Here you can see a list of these effects. Basically, all of them are very difficult to estimate correctly because they require complex finite element models and are time consuming. One of the most common way of dealing with them is to skip the computation task and use some kind of correction coefficient coming from experience on all designs. But this is really dangerous. In Spin, we have been spending a lot of time in developing easy and fast methods to investigate these matters. And many of them are already available in our Swift software, or for example, also in Flux Motor by Altair, with which we cooperate. But let me talk a little bit more in detail on these items. Let's start with high frequency losses due to proximity and skin effect, which we normally call AC losses. In the past, their impact on performance was considered negligible due to the low frequency of magnetic field. But today, they can greatly increase the amount of loss at high speed, as you can see in the upper right graph here. Proximity and skin effect can modify the distribution of current in the cross-section of conductors and also generate circulating currents. In some cases, the effect is so heavy that the motor must be derated at high speed in order to avoid damage due to a high temperature. As you can see in the lower right graph, AC losses can be reduced by properly designing the winding and selecting the correct shape, size, and position of wires in the slot. Another critical factor is related with eddy currents in the permanent magnets. Also in this case, high frequency and high flux density can lead to additional losses, this time located on the rotating parts, which are far more difficult to cool down. High temperatures on the magnets can also lead to demagnetization, which can make the motor useless in an instant. Eddy current losses are a function not only of the speed of the machine, but also of many factors like higher order harmonics in the magnetic field and in the supplied current, as well as the geometry, shape, size, and position of the magnets. One of the common ways to reduce these losses is to introduce segmentation. You can see a picture in the right part of the screen. Its impact is remarkable, but the resulting motor will be more expensive and difficult to build. So the problem is always to find a trade-off between loss reduction and cost of the motor. Well, high frequency and high flux density in modern motors raises a lot of issues also on ion losses. Despite the widespread availability of high-performance motors, the estimation of these losses is most of the time made using the old Bertotti formulation, which is best suited for sine wave and low-frequency applications. Anyway, the estimation is rarely accurate, and the introduction of correction factors based on all the existing motors is a common practice among engineers. Spin has been making a lot of work to define better methods, and today we can benefit from a new improved Bertotti model that leads to more accurate results. In addition, we have another method called loss surface model, which can estimate ion losses taking into account the effect of higher order harmonics. Both methods rely on a good characterization of soft magnetic materials, especially taking into account the effect of the manufacturing technology used to produce the lamination stacks, like punching, cutting, and stacking. Regarding this last point, let me add something very interesting. In Spin, we have a test laboratory specifically built to measure the magnetic properties of materials. We will show our testing capabilities during the last webinar of this series. But here, I just want to show an example of deviation of material properties due to the effect of the manufacturing technology of the stator. In this graph, you can see the BH curve of a lamination taken from the catalog. This is the property of the raw material. Then you can see the actual value resulting from the test on the final stator, the green curve. This deviation must be considered when designing a motor in order to achieve a good accuracy. Now, let's move on to another important aspect, which is the PWM effect. Synchronous as well as many asynchronous motors are always fed by inverters, having different control strategies. As a result, the supplied current is not a perfect sine wave, but is somewhat distorted, as in this diagram. In other words, it carries high order harmonics, whose effect can be found on all the losses described above. As an example, look at the table below. You can see how important is the increase in magnet loss due to eddy currents and also in ion loss. This increase is, of course, due to the distortion of the phase current with respect to the perfect sine wave, and is a function of the control strategy, together with a coupling between the electric parameters of the motor and the power supply unit. The same impact can be seen on AC losses, although they are not shown here. The good design of the motor cannot be achieved without considering the real match between the motor and the power converter, which can significantly modify the harmonic content of the phase current. Now, let me hand over the microphone to Sylvester, who will talk about another important factor, which is NVH and dynamic behavior of electric motors.
Thank you, Luigi. So I will share the document again. Okay, talking about PWM, it's the good moment, the good opportunity also to talk about NVH, because PWM have also a big impact on the noise and vibration of an electric motor. So here you can see an example of acoustic signature of an electric motor as a function of the speed and the frequency. The red line here correspond to the harmonics in the signature. So this picture is for a pure sinusoidal current. But if you switch to a PWM control strategy, you will find this kind of signature with more harmonics, and especially the characteristic harmonics we can call the water jet, which is due to the PWM. Sorry. You can also, of course, during the design phase, integrate this PWM into the simulation to have the proper signature of the electric motor. So the question is, why do we find some PWM harmonics into the signature of an electric motor? Let's go back a few seconds to the basics. So first we have to understand why an electric motor generates vibration and noise. So at the beginning, there is an interaction, a flux interaction between the rotor and the stator. And this flux interaction is generating some force we call Maxwell pressure in the air gap, so in the area between the rotor and the stator. This Maxwell pressure is depending, of course, on the time and also on the space, and depending on the coincidence with natural frequency, this excitation applied on the stator will generate more or less vibration and noise. Now let's have a look at the components of B. B is composed of air gap permeance, current, and windings. Also, these three parameters are also used by the electrical engineer to design the machine. For example, if you talk about PWM, as Luigi said, using a PWM strategy, we'll add some harmonics in the current. So these harmonics in the current will be also found in B, in the flux density, so in the Maxwell pressure, so in the excitation on the stator, and at the end, we will find it in the noise and vibration of the electric motor. That's why the electromechanical design and the NVH design, cannot be managed separately. I will say even more, they have to be managed at the same time to avoid issues. So I will show you an example of a real case. So here you can see a synchronous generator for automotive application. It's a really good design with high efficiency, good power density, low torque ripple. Okay, perfect electromagnetic design. And during the design phase, no one cared about the vibration and noise because this machine is supposed to work close to a running diesel engine. So with the noise already coming from the engine, no one concerned about the noise of this electric machine. But the first time it was put on the test bench, it started to vibrate so heavily that the vibration extended to all the system, so that the customer rejected the motor and threatened to rescind from the contract. And so Spin was called to investigate the problem and found that the reason for the vibration was actually the electromagnetic force applied to the rotor. And the only way to solve the problem was to completely change the design by modifying the number of poles and the number of slots. Of course, you can imagine that the cost of this kind of modification is huge, and also the delay on the project. And it could have been avoided if the NVH problem had been integrated at the beginning of the design process. So how can you perform some multi-physical design? It's not so easy, because you have to integrate a lot of physics, electromagnetic design, thermal design, mechanical design, and NVH. The starting point is always the same. We always start with the electromagnetic model to calculate the performance of the motor and also to estimate the losses. Second point and second phase, it's to the verification of the working temperature of the main part of the motors, as the winding, the permanent magnets, the bearing, and so on. As Luigi has already presented, the thermal analysis is probably one of the most difficult tasks to achieve. A lot of calibration must be done in order to fine-tune the actual heat exchange coefficient. This is the reason why engineers often use simple thermal models to get a rough idea of what the temperature will be. And then they move on testing on prototype to define the design. And this is normally expensive and time-consuming. And as Luigi said, there are some possibility to develop advanced thermal modeling, combining, for example, finite element model and CFD to make a good first calibration and to spend more time and less time and less money on prototype validation. Once the thermal aspect is managed, then you have to check also the mechanical model, especially in the most critical region, the rotor, especially when you have internal magnet like this design. And at the same time, you can also perform NVH simulation to be sure that you will match the NVH target. And if you validate structural reliability and NVH, then it means that you have the right design, the best compromise. Of course, you will need to validate all this model and estimation on the test bench, but if the job is well done in this multiphysical design, you will reduce the number of prototypes, and the time spent on the validation. Let's say also that this kind of process can be done with automatic tools to make some optimization, automatic optimization, and we will talk about this during the webinar number 4 of the series. Now, let's point out something important. The difference between, I should say, a good motor and a bad motor, whatever the performance or the NVH, is a matter of details. So here, it's an example you can see here a collection of power curves of the same motor obtained by simply modifying a few geometrical parameters, as shown in this picture. Also, the topology and overall size of the motor is always the same. You can see that the output power can be significantly different, especially at high speed, by slightly changing the magnet properties and the thickness of the small bridge and ribs in the design. So this is for the performance, but we could say the same thing for noise and vibration. So I have an example here. So on this picture, you can see the sum power level of an electric motor as a function of the speed. There are two different curves which correspond to two different designs. And in this case, we change the shape of the rotor. And you can see that between these two curves, you can have between 5 to 15, almost 15 dB of difference. But if we are talking about the geometry, where between these two curves, there are only a few tenths of millimeters. So it means that when you design an electric motor in an industrial process, you will have to take care about the sensitivity and the robustness of your design to avoid the dispersion. And it's not so easy. Let's conclude this webinar with some words about other sources of noise and vibration. And today we would like to focus on the rotor dynamics. And we will start also with an example. So this is an e-drive for motorsport application. Once again, the electromagnetic design is quite good, high power density, impressive performance. And once again, everyone was happy about the performance and no one thought to verify the vibration behavior. But when this motor was put on the test bench in order to set up the controller, suddenly during a ramp-up speed, a heavy vibration was triggered by some unknown cause. And it was always happening at a specific speed. And the Spin was called to investigate the problem, and they found an easy solution by checking carefully the resonant frequency of the system and moving them out of the forcing frequency. Of course, it implies a modification of the mechanical design. The solution never comes for free. So what could happen about rotor dynamics in electric motors? Let's have a few words about this. So we take the example of rotor eccentricities. It's difficult to avoid rotor eccentricities in an electric machine. And rotor eccentricities have two main consequences. The first one is a magnetic imbalance. It means that the Maxwell pressure is not evenly distributed around the circumference of the stator. And the second consequence is a mechanical imbalance. So it's corresponding to a rotating force applied on the rotor. And of course, it will have a consequence on the dynamic behavior of the driveline, especially if you excite, for example, some bending modes of the rotor. Here you have some example of dynamic response of rotors under rotor eccentricity excitation. So for radial flux machine and axial flux machine. But rotor eccentricity have also some consequence of the noise. So here you can see some noise signature of electric motors. always as a function of speed and frequency. So on the left, it's the machine without eccentricity. And you can see the harmonics corresponding to the magnetic excitation. Sometimes you can find some high level due to coincidence between the excitation and the natural frequency of the electric motor. But if you look at a machine with eccentricity, you will find more harmonics in the signature, mainly corresponding to the modulation of the main harmonics, magnetic harmonics. So rotor eccentricity will change the signature of the electric machine. And when you measure, so this is simulation, but when you measure the noise and vibration of electric machine, you will find more this kind of signature on the right than this perfect kind of signature on the left. Last word about mechanical source. So we choose to present you the gear noise. So because electric motors are very often associated with a gear transmission or gear system. It can be spur gear, helical gear, or also planetary gears. And all these systems are generating pulsating force due to the contact between the teeth, and they have also their own dynamic behavior. And if you want to get the full signature of your e-motors, of your e-powertrain, sorry, you need to have a model for this transmission. I will give you an example. So this is the signature of electric motor alone. This is a simulation. So you can see here only the contribution due to the electromagnetic excitation. And if you do the same simulation, but with the integration of the transmission, you will find this kind of signature. So it's very important also if you want to have an overview of the noise and vibration of your e-powertrain to take into account the transmission. Okay, so this is all for the introduction. Of course, all the topic of today will be deeper addressed in the next webinar. We hope that this presentation will make you want to follow our next episode. You can find the program here below. So it's easy to remember. So our webinars are organized each Tuesdays at 2 o'clock in the afternoon during the next 4 weeks. And here you can have the program. So the next one is about electromechanical design. So, and then it will be about the NVH design of e-powertrain on February the 16th. Then we will do a special webinar on multiphysical optimization with innovative methods. And finally, on the 2nd of March, we will present you some methods to validate the performance and the noise of vibration on your test bench. So thank you, and I think we have time to answer your question in the chat. So let's go to see if there are some questions. So we have a question about the test bench. Does the third webinar encompass how to make a setup bench for NVH analysis? So this will be addressed in the fifth webinar, not in the third webinar, but we're gonna talk about this. And third webinar will be more about the noise and vibration of the electric powertrain. Okay. Any other question? You can also ask it in Italian if you want, or in French. Stefan, yes, you will have access to the, I think, to the slide of the introduction. So the question is, can we please have access to the slide? So I think that we will share the slide of this first webinar. And then for the next webinar, what we do is organize a replay session, not for free, but you can access to replay session. Another question. Do you consider effect of magnet temperature on NVH behavior of Emachine? And what is the usual temperature considered for electromagnetic force calculation? Maybe we can have a combined answer with Luigi on this point.
Yep. Yes, sure. It's a good question from my point of view. Well, it depends, and there is not a single temperature on which you want to calculate electromagnetic forces and something related with NVH. You can make it in different temperatures. Of course, we are when we are involved in the design of motors for automotive application, then we tend to compute forces in all the temperatures, considering the overall range of application of the motor. So, of course, when we make this kind of computation, the temperature of the magnet is updated correctly with the working temperature at which the motor operates in that particular case. So you can modify the properties of the magnet and find the correlation with the force. And it is a huge correlation because when you modify the temperature of the magnet, then induction across the air gap is completely different. It's a huge impact.
And another question also from Marco Fraternali. I think it's for Luigi. When you talk about calibration for the thermal model, does it involve a physical prototype or is it all with virtual models of the motor?
Well, both. I think, first of all, we make calibration using virtual models before to make a prototype, because we want to shorten the time that we spend to go to make a prototype and test. So we make both finite element and CFD analysis to check the heat transfer coefficients and calibrate the model. After that, we build the prototype and make measurements, and we fine-tune the model with actual test data. Both are necessary because, as I said, thermal analysis is the most difficult and calibration is always needed. There are a lot of parameters involved in the actual temperature that you measure on the motor. So both are necessary.
Okay, another question from Mohamed Farouk Ababou. Hello, Mohamed. Nice to see you again. Is the NVH analysis considered in your episode is only about the e-motors element, or do you plan also to see the effect of e-motor vibration and its propagation through the vehicle structure? Also, no, so sorry, but this time, in fact, in our last webinar series, we talk about the integration of electric powertrain in the vehicle, but this time there is no webinar planned for this topic. But you can find a replay of our webinar, so you can ask to me if you want to have this replay about the integration of electric motors in the vehicle structure. Another question from Pradip Singh. Is it possible to share some analysis done to identify sensitivity of NVH towards magnet temperature for permanent magnet synchronous motor?
Well, it is possible, of course, but we need to identify which is the motor subject of the analysis, because it also depends on the motor. Most of the time we make analysis for our customer and we have strong NDA requirements, so we are not allowed to disclose the content of the analysis, but we can make some sort of demo examples to show the sensitivity. It is something that we can talk about. If you want information, we can talk about that privately, no problem.
Okay. And another question from Giuseppe Zanocci. Sorry for the name. What are the other sources of vibration and noise in an electric rotating machine beside the electromagnetic ones? So there are also the aerodynamic sources, the mechanical sources, for example, the bearings. Also, what is related to the transmission also. So it can be gear noise, and I think that's all. And there is also, yes, of course the impact of the power supply, but this can be considered as electromagnetic excitation. Thanks. Okay. Thank you to you. Any other question? Okay. So don't forget the webinar next week about the electromagnetic design of Emachine. I think you will be the speaker, Luigi.
No, there will be other speakers from Spin, expert in designing electric motors and specifically in the topics of the webinar. So we will have Alberto Rubino and Alex Quantelli hosting the webinar.
Okay. So if there is no other question, we hope to see you on. There is Daniele. People, don't hesitate to write something, or we will close the session for today. Okay, so people are writing. Thanks. Thank you to you also to attend this webinar, and see you on next week.
Thank you all, and see you next time.
Yeah. Bye-bye. Thanks for your message.